Okay, so thanks everyone for joining today. And thank you very much to Professor Barcanova for the invitation to give a talk in this series of seminars about quantum science and technology. So I'm excited to talk to you this morning for a little while. And the topic of my talk is going to be basically about patterns, probabilities, and particles. I'm going to be talking a little bit about quantum mechanics and also about the work that I do in particle physics at the Large Hadron Collider at CERN. But first of all, I was asked to talk a little bit about where I'm from and how I got to where I am. So I'm going to start with that part of the story. So there are some pictures in this part of the talk. So this is a picture of me, actually. So this is really where I'm from, right? So I grew up near Halifax, Nova Scotia. I'm actually from a small fishing village south of Halifax called Sambro. So my dad was a lobster fisherman, and my mom stayed at home to raise my brother and I, and then went back to be a librarian at school when we got a little older. So I'm actually the first person in my family to get a university degree, but I'm not the last. So actually, my brother also has a science degree from the University of Cape Breton. And my brother also he works and lives most of the time on a boat. So he's in the Canadian Coast Guard. So my dad and my brother have boats, and my mom and I have books, right? So you can see who I take over, who I take after. Um, this is a picture of my dad's boat and my brother's boat. So this is the Molly Cool. So he spends part of his time actually up on the northern coast of Newfoundland, so breaking ice. He goes back and forth between a couple of ships, but he is in Newfoundland most of the time, actually. Cool. So after I graduated from high school, and it's a treat today, actually, so my high school is connected, so it's great to see people there. I applied to a few different universities, and I wound up going to Acadia University. So this decision was mainly made due to available financial aid from Acadia. So, that was important for me when I was making my choice. And actually, I wound up applying to university early on in chemistry. And I switched to physics upon getting there. It turned out that the parts of chemistry that I liked were actually quantum mechanics. And Mr. Turton, who's connected, helped set me straight on that. So by the time I got to Acadia, I was already a physics major. But sort of after that, I stuck with physics ever sort of, until now. Um, I even spent a summer actually working in the lab for Professor Barcanova. So this is a picture of me at Acadia, putting together a radon measurement device. We were studying radon levels in people's homes there. And then after a couple of years at Acadia, working there for the summer doing research, I decided that I wanted to try to strike out more broadly. And there had been a student the year ahead of me who had done research at Triumph, which is a lab in Vancouver, the year before. So I applied to that program. But I wound up getting selected for that by a different group. And instead of going to Vancouver, I spent most of my summer at CERN. So this is a picture of all the people that I met that summer. So CERN is a particle physics lab on the border between Switzerland and France. I'm going to talk more about it in the later part of the talk. But you can see a couple hundred students that they have every year here. And if you look very closely, I'm somewhere near the middle of the photo. So this summer was really transformative for me. It was really exciting to be here in this group of people at this particular time. So in 2010, the Large Hadron Collider had just started taking data, actually just maybe a month before the summer students arrived there. And so we got to spend the summer following all the very first developments of the accelerator and sort of watching researchers rediscover particles in the standard model as time went on, which was cool. These are a few more pictures from that summer. So you can see that sometimes they let the summer students underground. That would be the picture on the right. Sometimes they let us only pretend that we're underground. So that's the picture on the top left, where it looks like I'm in the LHC tunnel, but it's actually a backdrop. And, the other picture on this slide, I just wanted to show these were the 5 Canadian summer students from that year. And in fact, even though it was 15 years ago now, I still interact with almost all of these people much more often than you think. So they're all still in academia. 4 of us are still in physics. The other one is a math professor at UBC. And several of us actually work in the same area at the LHC, which is maybe a coincidence, but it's also quite interesting to think, right, about the people that you meet along the way and how long you'll be interacting with them in your career. So after I got a taste of particle physics, that was more or less all that I wanted to do. So after I graduated from Acadia, I decided to pursue a PhD. I went to the University of Victoria to do that, and I continued working on Atlas during this time, which was the experiment that I had been a summer student on at CERN. So I spent some of my time during my PhD in Vancouver at Triumph, and then I moved to CERN later on for a couple of years. So on the left is a picture of me at my desk on Triumph that was actually on the CBC Evening News in July of 2012. So this is when the Higgs was discovered. I think I just happened to be sitting there at the time, and someone with a camera came through that day. And then on the right, this was a more deliberate place for me to be sitting. So this is me in the Atlas control room a couple of years later doing shifts for one of the detector systems as a graduate student. So after my PhD, I graduated and I was a postdoc for some time. I got to work with a lot of people from all over the world. So this is one of the groups that I did most of my work in when I was a member of Atlas. This is a picture of us all in 2022 at Cambridge University at a workshop. And the reason I like this picture is because everyone is lined up very neatly. So it's easy to do things like show all the different places that these people are from, right? So particle physics, as I'll try to explain this morning, is a very international and diverse field. You have to work with a lot of different people. You're not just sort of working alone in a lab. Most of the time you're in meetings or discussing or working with a team to achieve something fairly complicated. And it takes people from all over with different sets of skills to do that. So you can see there are sort of over 15 different countries that I've indicated here. And I've just put one flag for each person from one country, right? So there are more than one Canadian in this picture, for instance. Good. So this is where I am now. So these are a lot of the people that I work with day by day. So this is actually 2 research groups here at Brown, but we all study the same type of physics at the LHC. So you can see a lot of the students that are in my group in this photo, and then sort of about half of them collaborate with me directly, and the other half collaborate with Professor Roloff, who is standing stage right to me in the photograph. Cool. So the next part of the talk, I want to, anyway, I should say also before I start talking more about physics, that at the end of the talk, I'm happy to talk not only about physics and answer questions that you have about physics, but also sort of about my path or life as a particle physicist or working at CERN or anything like that. But now I want to talk a little bit more about quantum mechanics and then particle physics after that. So I think hopefully many of you are familiar with the idea that, we or our pets, sort of macroscopic objects, are made of cells, and cells are made of molecules. Molecules are made of atoms, right? You may have learned this in your science or in your chemistry classes at some point in school. Hopefully you know that atoms are made of smaller things, right? So atoms are made typically of protons and neutrons in the nucleus, which is a small sort of hard bit of the atom in the center, and then electrons orbit around that somehow. And something that you may or may not know is that protons and neutrons are actually made of even smaller things, right? So protons and neutrons are made of funny named particles called quarks and gluons, which are also themselves very small. As far as we can tell, electrons and quarks aren't made of anything that we can detect, at least at the moment. So they seem to be point-like particles. So if you're wondering about how a proton is made of quarks and gluons, then I have this example from an event that we were doing at CERN, where people came to an open house at the lab. So protons are made of 3 different quarks. So 2 up quarks and a down quark combined in a certain way to give you a proton with the properties that you know, right? So a charge of +1, for instance, and they're stuck together with the gluon. So you can make a proton cookie if you want by putting some gluon icing on it to keep the quarks stuck together, and then putting 3 quarks on the cookie. Of course, these quarks also have a different color, which is important, which I won't probably talk much about right now. So protons are the kinds of particles that we collide at the LHC, which is why they're important later on in this talk. So now I want to talk a little bit about one of the differences between physics at sort of everyday scales and physics at the quantum scale, right? So one thing that you'll learn in physics in high school is that physics lets you predict the future, right? So you'll learn things like if something goes up, usually it will come down eventually. One of the first things you learn in a physics class is about projectile motions. You'll learn that, if you throw a ball, or here there's this water jet in a fountain that goes up and comes down, that it will follow a parabola. So you can learn the equation that describes its height and time, for instance, which I've put on this slide. And you could do things like predict how long the ball will be in the air, how far it will go, if you know the angle it was thrown at, things like this. This is all useful. It lets you do very impressive things, like make a basket from the top of a very tall building. So you can tell that the guy throwing the ball paid attention in his physics class. But when we get to smaller scales, these classical laws kind of break down, right? So when we enter the quantum realm, we can't rely on our intuition from everyday physics anymore. So one difference that I wanted to highlight here is that you can't predict the outcome of a quantum event. You can only predict the chance of something that might happen, right? So one example that I could show to explain a bit what I'm talking about is if you take a little box and put a marble in it, and classically, you know where in the box the marble is, right? Especially if it's not moving around, it's just in one spot, it's easy. But in quantum mechanics, if you took a box, so here I have a sort of 2-dimensional box, then I'm going to put a particle in it. You never know exactly where that particle is until you look, right? So if you look many times, you could have some intuition for where you think the particle is most likely to be. So I've put the expectation for an electron in a quantum box here. This is the red line. So you can see, I think the particle will more likely be in the center of the box than towards the sides. But any given time that I look, I'm never sure exactly where it's going to be until I've looked. And so I can start looking. And if I make observations here, you can see the blue distribution of observations stack up. And once I make 10,000 or so in this example, then you can see that most of the time when we look, the particle is in the center of the box, and sometimes it is out towards the edges, right? So if you want to have some understanding of a quantum process, often you want to look at it many times, which is what we do in particle physics, and it's why we have sort of big machines that deliver a lot of data. So today, I think, in the next part of the talk, I want to describe a little bit the journey through some of the history of particle physics, to explain a little bit about why we have experiments like the LHC operating in the world today. And when I start by telling a story, actually, about physicists who like to walk and think about clouds. So this is Charles Wilson on the right side of the slide. And in the background of the slide, you can see a photo of Ben Nevis, which is a mountain in Scotland. Professor Wilson used to work at a research station, an observatory that was up in the mountains in Scotland. So he would go walking up there. And one day while he was walking, he actually became interested in cloud formation and sort of things that could happen when um, you are looking at clouds in the mountains. This is probably because this photo was taken on a clear day, but a lot of the time in Scotland, it's a bit cloudier. So the story goes, he saw something like this, which is a sort of optical illusion or an optical phenomena called a Brocken spectrum. So the sun was behind him, and he was sort of in the cloud, so you could see his own shadow projected into the cloud in a funny way, which inspired him. And so Wilson went to design a chamber. He wanted to be able to study these topics in the lab, particularly cloud formation. So he wanted to make clouds. And this was in 1894, right? So it was a bit tricky back then to make clouds whenever you wanted. But he figured out a way. So this is his original cloud chamber. So this is in a lab in Cambridge in the UK now. And it's basically a couple of volumes and a chamber where the pressure in the chamber could be changed very quickly. By doing this, it would make a cloud form. So this is something you may be familiar with if you've ever pressurized a bottle with a little bit of water in it. So we can see this example work. So in this plastic bottle, there's a little bit of water inside. And by making the volume of the bottle smaller, you can pop the top off, right? Which is maybe a trick you've done at some point in school. And when the top pops off, a bunch of water vapor forms in the bottle. So it makes a cloud. Sometimes if you open like a soda bottle, right, you'll see a little cloud at the top. So Wilson figured out a way to make clouds in the lab, so he was happy. And it turned out that this invention also made a lot of particle physicists happy because it revealed this sort of subatomic world of particles whizzing around us all the time. So this is a sort of modern day video of what's going on in a cloud chamber at a particle physics lab. And you can see these little streak-like clouds being produced by particles that otherwise, without this type of detector, you are unaware of. It turns out that some of these particles come from background radiation that's sort of around us in the world all the time. And some of them come from cosmic rays. So these are actually particles that are produced in showers from outer space, which you can detect with this type of experiment. So a cosmic ray, yeah, this is just a sort of side note, but it's actually not too difficult to make your own cloud chamber. So this is an activity I used to do with the physics lab at UVic when I was a TA doing my PhD there. And CERN has a lot of interesting resources for how to make a cloud chamber online. So you basically need a little bit of ethyl alcohol like you would have in a physics lab, some dry ice, and a heat lamp. And you can get this to work if you have a container that you can close quite firmly. So what is a cosmic ray? So I said these are particles that are coming from space, right? They're showering. What did I mean by that? So this is a visualization of what a cosmic ray shower might look like. So these start in the upper atmosphere when high energy particles from outer space, so these are produced outside of the solar system, then they hit the Earth's atmosphere, and this collision, because they have such a high energy, starts a huge cascade of other types of particles. And some of these even reach the ground, right? So this is what we were detecting in the cloud chamber. So you may have some familiarity with the idea of particles hitting the Earth's atmosphere and making things happen. I know in some northern regions in Canada, you sometimes see the northern lights. I think most recently, just a few days ago, it was quite visible, actually, even down here in Rhode Island, where I am right now. So the northern lights are caused by particles from the sun, which hit the Earth's atmosphere and ionize it to make it glow. And then cosmic rays are showers of particles that come from outside of the solar system, right? So the particle starts in a different source further away, and then it travels through space until it hits the Earth in showers. So over time, by studying cosmic rays, people made a lot of discoveries. So sort of in the first half of the 20th century, by studying cosmic rays at first on the ground, and then by putting experiments higher and higher, climbing mountains with cosmic ray experiments, sending them into the atmosphere on balloons. Several different particles were discovered. This is actually how the first evidence for antimatter was collected. So the anti-electron or the positron was observed in a cloud chamber, basically produced by cosmic rays. A heavier copy of the electron called the muon was also discovered this way in the same lab in Caltech in the 30s. And then, as I said, some other particles were discovered by sort of going up higher into the atmosphere because the types of particles that are produced in the cosmic ray shower depend on how high up you go. Some of them don't last long enough to reach the ground. So muons and positrons do, but in this sort of picture on the right side of the slide, you can see how by going up into the upper atmosphere, you can access some parts of the shower that look a little different, right? So this was an adventurous time for particle physics. People, as I said, made a lot of discoveries by using cosmic rays. But at some point, we needed to collect more data. So it's impossible to predict what might happen in any given event. So you need a lot of cosmic ray data if you want to see rare things. And cosmic rays hit the atmosphere something like, once a second per square meter. So it's not so fast if you want to see rare quantum processes. And so on this slide, I have two pictures of data from the top one is from a cosmic ray experiment. So this is from an experiment where people were actually climbing mountains in France, in the Pyrenees. And later they took them to Bolivia to get a little higher. And they would run their experiments for weeks and they would get a handful of data events. So I think in the paper where this image is from, they had 60 or 80, sort of less than 100 good data events from running their experiment like this, which was a lot of work. But then about a year later, at a lab in Berkeley in California, people figured out how to make exactly the same particle that had been discovered by these researchers in Bristol, but they could make it 100 million times faster. And this was basically by making a machine that would produce particle collisions at a much higher rate in the lab, right? So we sort of moved from cosmic rays to studying collisions that we had full control over. And this is a cartoon on the left side of the slide that shows you what I mean by this, right? So if we could sort of speed particles up and smash them into something, make a collision, then we could look at what comes out and we could look at much more data than the cosmic rays allow us to study. So I just have a couple of slides that show you some early accelerators. So this is an early linear accelerator at CERN. So the particles would come sort of straight down the middle here. There's a person tuning it up so you can see the scale of this accelerator. So this was, I believe, LINAC 1 at CERN. So this operated from 1958 to 1992. It's in the museum there now. And people made, over time, very long linear accelerators. So this is a picture from a plane of the linear accelerator at Stanford. So this is in the Bay Area. You can see in the background of the photo, San Jose is sort of there in the upper right corner of the slide. And then if you went to the left up the Bay, you would come to San Francisco and Berkeley, right? So the linear accelerator is shown sort of top to bottom. It's about 3.2 kilometers long. It's, a kind of incredible feat of engineering. And it did a lot of interesting physics during the 90s. So it started taking data in 89 and went for just about 10 years. And it's still being used for scientific purposes, but not for particle physics collisions anymore. It's being used for a different kind of science. So the problem with linear accelerators is that they get very big, right? So also in the 30s, at Berkeley, as I mentioned, researchers figured out how to make accelerators that were smaller, so they would fit in a lab by making them circular. And this is a drawing of the initial patent for this type of machine, 1934. And then only 5 years later, they had a working prototype in the radiation lab at Berkeley. So the speed with which they built this, I find incredible as someone that works in particle physics today. And if anyone connected has seen Oppenheimer, this machine that's photographed is actually what Josh Hartnett is making in the lab at the start of the movie, the 1.5-meter cyclotron. I wanted to mention cyclotrons because there's a nice connection to Canada here. So a cyclotron, or this kind of circular accelerator, is the type of accelerator that in Canada we have a triumph, right? So the 18-meter cyclotron, just pictured here under construction, so you can see all these people that were working on it in 72, is sort of one of the largest cyclotrons in the world. And it is, you know, a really useful major piece of scientific infrastructure that we have in Canada. One fun fact, actually, about the Triumph cyclotrons, so these big metal pieces that the people are sitting on in this photograph, these are called Ds, so these are like the electrodes of the accelerator. And the reason that I wanted to mention these, so normally these are covered up, but they were actually made at a shipyard. So these pieces of metal were too big for any normal machine shop to manufacture. So they had to be made at a shipyard in British Columbia and brought to the lab in Vancouver. And the shipyard actually also provided a ship's steering wheel, which is customary. If you make a ship, you give a steering wheel as well. And that steering wheel is hanging up in Triumph in one of the lecture halls to this day. So going from the 20-meter cyclotron to something that's even larger, this is a photo of the Large Hadron Collider at CERN. So it's 27 kilometers around. And this is the accelerator that I work on actually today. So it is taking data even right now. We're almost done with the data taking run for the year. And you can see here it's superimposed over this photo of the area between Switzerland and France. So France is closer to us, and then in the background is Switzerland. So you can see the Alps in the distance in the back of the photograph. And there's a big lake, which is Lake Geneva. So at some point here, you can see my old apartment. If you zoomed in really far on the city at the end of the lake. And then CERN is located just a little distance away. Near the label that says LHCb, you can see there's like an airport, which also gives you some scale for this photograph. And then the main CERN campus is sort of on the left side of the ring. Of course, this isn't actually the LHC. The LHC is underground here, about 100 meters. And it has 4 major detectors on it. So they're called LHCb, ELISE, there's ATLAS, which is the experiment I used to work on, and there's CMS on the opposite side of the ring, which is the experiment that I work on today. So hopefully this works. It did not. So I might try to show a video here on YouTube. Could you confirm that you can see the other window?
I only see RGB sliders.
Only RGB sliders. Okay. Maybe we will not. Oh, I see what's happening. Okay. Okay. So I think we can't see the video. I'm sorry about that. So this was supposed to be a video of an LHC collision taking place inside of Atlas, but I can post the link to this afterwards. But the LHC essentially accelerates particles and smashes them together 40 million times a second, which is what I was going to tell you while the video was playing. And so by taking collisions this often, we can actually collect huge statistics of data to study really rare quantum processes at the LHC at high energies. Okay. So if we want to study these collisions, and I'll show you a picture of what one looks like in a couple of slides, you'll have to sort of stay tuned for that maybe. We have to have big detectors. So this is a photo of the CMS detector. At the very bottom of the slide, next to the cherry picker lift, you can see a person who's actually taking a picture up of CMS, right? So she's at the bottom in like white pants and a black shirt. So these detectors are enormous. They're in caverns the size of cathedrals underground, built more or less like ships in a bottle. So the pieces are lowered down through shafts in the ceiling and then put together in the cavern. And basically, what these are is something like a huge camera, right? So every time the LHC collides protons, this detector produces an image of it 40 million times a second, and then we have to decide which ones are interesting for further study. So this means that we have a lot of data to deal with. So CMS records something like 1,000 megabytes of data per second. And there's something like 150 petabytes of data produced by the LHC. So a petabyte is 1,000 terabytes. And if you don't know what a terabyte is, but you know what an iPhone is, the most iPhones have a quarter terabyte of storage, right? So we're talking about a lot of iPhones of data in just 1 year of LHC data taking. This is a similar amount of data to the amount of data that's uploaded to YouTube or to Facebook in about a year, right? It's similar, especially if you consider the amount of simulations. So we collect all of this data with the LHC, but we also have to run a lot of theoretical simulations to interpret the data that we're collecting, which takes up almost as much space as the data does in the first place, right? Now, this amount of data is what we choose to keep, but we keep only a small subset of the collisions from the LHC that we think are the most interesting ones. So imagine if we were looking at 40 million photos a second, but we had to delete 39,999,000 of them right away without looking at them any longer, right? So this is a sort of enormous challenge in data science as well as in particle physics and computer science. And even by deleting, or by not recording so much of the data, we still have this huge data set to play with. So for these reasons and for others, right, to analyze this large data set, particle physicists were early adopters of artificial intelligence and machine learning methods, which we're still using today, I think more than ever, to find interesting patterns in the data. And I'm happy to talk a bit about that at the end of the talk as well. So this is something that I work on here at Brown, not only with physics students, but also with students from the engineering department and computer science as well. So one fun thing about all of this data is that the most cost-effective way to store it is to store it on tape. And because it's on tape, the raw data, you have to go and get the tape and read it out if you want to look at a specific bit of data for analysis. And so we have these robotic helpers that actually move around the tape racks and get the data that's requested by users, like the one that's shown on this slide. Okay. So I just wanted to finish up by saying a few words about how these detectors work. So like I mentioned before, they're basically like giant cameras that make an image of each LHC collision. And different kinds of particles that are produced in the collisions leave different signatures in the detector that allow us to identify them. So the one that I wanted to highlight here, which is sort of the easiest one to see, is the muons. And this is one of those particles that were discovered, about 100 years ago or more in, not quite 100 years ago, actually, in cosmic ray experiments. which is the blue line here. So this is a cutaway side view of CMS that shows all the different pieces of the detector. And the blue line is the muon that starts in the middle, and then it goes all the way out through the outer part of the detector. And it leaves signal the whole way. And so it's easy to tell this one apart from other types of particles that stop in the innermost layers. So here's a photo of CMS again, taken sort of looking face on in the detector, and you can see two muons drawn on it as they would look, right? And the pieces of the detector that they would leave signals in are highlighted with the red boxes. So they go through the innermost part, where there are also all these orange particles, but the red ones are the only ones that go all the way through the outside and leave hits there as well. So it makes them easy to see. This means that events with muons are easy to pick out, right? So this is a picture of what the first collision event that we took this year looks like. It kind of looks like a big mess of particles inside of the detector, but there doesn't appear to be, at first glance at least, anything remarkable about this collision. It just happened to be the first one that we recorded in 2025. This is the second one, right? It looks a lot like the first one. And actually, most LHC collisions look something like this. This one's much more interesting. So in this collision, you can see 4 muons coming out of the collision, and they all leave hits in this outer part of the detector that's used for muon detection. So this event is actually an image of a Higgs decaying to 4 muons. So Higgs bosons are one of the very rare particles that we want to study at the LHC. And they can decay to many other types of particles. In particular, they can decay to 4 muons, but only very rarely. So out of the sort of trillions of collisions that we take in any given year, we might make a couple million Higgs bosons, and we really want to try to pick these ones out and record them for further study. But even out of all those Higgses, only about 1 in 1,000 will decay in this channel, right? You never know, because the Higgs decay is a quantum process, what channel, like how it will decay. And so you just have to record enough that you can collect enough Higgs decays that you can also see it in a channel like this, which is very easy to pick out. So this is one of the reasons that we need to take a lot of data at the LHC. So to finish up, I have one more animation. So this will show you, it might remind you a little bit of the particle in a box animation that I had before, but this is actually showing a distribution where you can see a sign of the Higgs decay to 4 muons in it. When we were thinking about the electron in the box, I had this red line, which was our expectation, right? So I said it should be in the center more than on the edges. And in this distribution, the blue line is our expectation without the Higgs, right? What we're seeing is actually data that was collected over the first couple of years at the LHC operating, slowly piling up over time. So there's 2 years of data that goes into this plot. And these are really individual data events that you're seeing get included here from these Higgs decays to 4 muons, right? So the blue part is stuff that we thought was already there, right? But then there's also this red peak that pops up above it, which the blue line doesn't explain. And this is actually the signature of the Higgs boson. So in 2 years of data taking, we had enough decays in this channel that by the end of it, I'll let it play one more time maybe. By the end of this data taking, there are enough decays here that you can say confidently that we are observing something that the background cannot explain, and this is a particle that we have gone on to understand seems to be the Higgs boson, right? So you may have heard about this discovery that was made at the LHC. Okay, so just to finish up, I've already mentioned that particle physics is a sort of huge endeavor. It involves people all over the world. I wanted to show also, these are a couple of photos of the collaboration that I'm a member of now. So on the right is a photo of a bunch of people from CMS who are at CERN for a meeting in one of the halls. I believe that this hall was one that was used to assemble. No, this is at point 5. Anyway, so, this is a bunch of people that work on this experiment. And then on the left shows you a map of all the different countries around the world where people are from, right? So there are over 4,000 members in CMS. About half of those people are fairly young, so they're students and postdocs. They come from over 240 institutions, so these are different universities and labs around the world, and in 50 countries. So unfortunately, Canada is not a member of CMS, but it is a member of ATLAS, right? So ATLAS and CMS are sort of two general purpose experiments at the LHC, which are probing similar types of physics. ATLAS is a similar size, but just a different mix of people. Good. So to finish up, hopefully I've convinced you that particle physics requires a lot of hard work and collaboration by a lot of people all over the world. I told you a story about how new types of detectors allow us to see new types of particles. And hopefully I've also convinced you that if you're studying a quantum process or a particle physics process, that it's useful to have a sort of very large data set, right? Because you never can really be sure what a quantum particle is going to do. If you asked me when I was playing with this lobster on the kitchen floor, whether I would be a particle physicist when I grew up, well, I probably wouldn't have answered you, right? But if you'd asked me when I was a little older than that, I also probably would never have guessed that this is what I was going to end up doing. But, it's just, I think, some evidence that if you're interested in something and curious about it, you don't stop trying to learn, then you can do basically whatever you want, whether it's physics or, whatever you are curious in. So now I teach students about particle physics every day, and it's really a delight, right, to come to work and talk to people about physics all day.